Hello, something a little bit different today. About a year ago I did a video where we built this robotic arm, and it was lots of fun and it was quite different for the channel. I quite like tinkering about with embedded systems like this, but they're not the most accessible thing. I mean, the channel makes a lot of desktop software and that's easy and accessible for everybody to do. But as soon as you start wanting to try things in hardware, well, you need to spend a little bit of money. So I found a very cheap robot arm. It was available on Amazon. And the video was about how do we connect to it, how do we control it, and ultimately it ended up with some great silliness on the Twitch channel where I let the Twitch viewers via the chat control the arm, and they almost killed me with a screwdriver. I think occasionally it's good to do non-desktop software stuff, and so I was looking for another platform to make another series of embedded videos. And just as I was thinking about this, a company named Elegoo contacted me and offered me this Elegoo Smart Robot Car Kit 3.0 Plus. Now, full disclosure up front, they have sent this to me on the condition that I use it in a video at some point. So here we go. And it's my intention to have a look at this and build it up, and then program it to do something interesting. And I think by the time this video goes out, there'll be a link in the description below where you can get a reasonable discount on actually getting one of these for yourself. They're not very expensive, but they come with all of the parts necessary to make a motorised platform that's got a handful of sensors on it. It says here on the box that it's controlled by Bluetooth. It's got line tracking sensors, so I'm guessing some sort of light sensor. It's got obstacle avoidance, which I'm guessing these cute little eyes here are actually an ultrasonic sensor. And it can be controlled via infrared remote control. Fundamentally, the platform sports a small Arduino. And I'm hoping it's included because everything is powered off a 7.4 volt lithium battery. As of this moment, I haven't even opened it up. So let's do that and let's see what's inside. It's quite exciting, isn't it? Oh, we get an assembly tutorial. I'll tip that round there so we can see what's going on. We get an assembly tutorial, Smart Robot Car Kit 3. We'll have a look at that in a minute. And we get some nice boxes. So I'll take these boxes out. Then we can get rid of the big cumbersome box. So here we have 4 boxes inside and an instruction manual. It says thank you for your support and purchasing Elegoo products. And then there's some assembly instructions, and we will follow this. We won't be all masculine and not bother. So let's start. It says, attention, remove protective film before assembling. Well, let's get all the parts out the box and actually see what they've provided for us. after I finished building this yesterday, I plugged in the battery and left it to charge overnight. So here we are, ready to see what it does. And it turns out that it's pre-programmed. And the program I'm interested in running is one controlled by this little remote control. So we'll finally get to see how fast is the car. Let's take a look. So I'm going to press the forward button here. Oh, yep, it's it's very fast. That's quite impressive. Now let's try turning it round and that way. I've not got any way of testing the ultrasonic sensor up here, so I think we need to go downstairs into the kitchen and give that a whirl. So I've come down to the One Lone Coder kitchen, where I've got a reasonably large flat stone floor. I'll just turn the car on, and I apologise for the guerrilla style shots we're doing. I'm recording on my phone. And I'll press the one... Well, actually, I won't press the one button, I'll press the forward button. Okay. Very nice. Give it a turn on the spot. Now, according to the instructions, yes, this is one of the frustrating parts, is it seems to turn 180 degrees each time. So once it's in a strange position, I can't do anything about it. So I'll just manually set that up again. And this time we'll try mode 2, which uses the ultrasonic sensor to avoid obstacles. Oh dear, off it goes onto my messy floor. So we can see that it's ultrasonically scanning in 3 different directions at once. That's quite a low resolution, so it will hit things that get in its way. The other problem with the ultrasound approach is that the sound reflects off the surfaces and not necessarily back into the receiver part of the sensor. I think it's quite cute. So far I've been controlling the car using the remote control, and that uses the infrared emitter and this little infrared sensor on here. It's only very small. But it's also controllable via Bluetooth, and here it is. This is the Bluetooth module, and they provide an application for your phone with which I presume you can do the same sort of thing. I'm not interested in installing that on my phone. But I did think it would be quite interesting to write an application to communicate from my PC with Bluetooth to try and control the car that way. After all, I did something very similar when we programmed the robotic arm. It was in fact wireless, except for the many wires controlling the power. And because this video is crudely interrupting a series about using ASIO to do thing-to-thing communications, then I thought, wouldn't it be appropriate to quickly look at how we can use ASIO to talk via Bluetooth to the car? The instruction manual that came with the car directed me towards download, where I can get lots of pre-made programs. So I thought I'd take a quick look at those, and we'll start with these in English. And they're structured in the form of lessons. So let's just take a quick look at making the car move, lesson 1. And they're quite nice lessons. Not only do they tell you how to build the car, but they tell you about the underlying technologies and terminologies used in controlling it. Lesson 2 is Bluetooth car, so I think we'll start there, just to get a quick feel for what's going on. So it tells us how to set it all up, and of course it uses the phone app, but that's what I want to try and avoid. I think the documentation is written very well. So we've seen in the past that we need to use something called pulse width modulation to control the movement, and it gives us a nice description of that. So I think if anybody that isn't familiar with these sort of things, the documentation is actually a good starting point. But more importantly for us, it comes with some source code. Now you'll need the Arduino programming environment for this, and I thought I'd have a look at the program called Bluetooth car. On the surface it seems very simple. We set some pins for the Arduino, we set the directions, and if we assume that this forward function means move the car forward, we can see we're sending some enable signals. We're displaying something back on a serial port, the word forward, and I would suspect that these 4 signals are something to do with the direction, and these 2 signals are something to do with the speed. That's backed up by the fact that when we look at the functions for left and right, we can see that we write to the same pins a value. So that will be sending some PWM value to the motors, because it looks like when they want to turn left and right, they want to reduce the speed of the wheels. Additionally, these pins indicate which wheels are turning and in what direction.
So we can see that when we're turning left, the low, high becomes high, low when we're turning right. The program itself is very simple. It sets up a UART with a baud rate of 9600, and we did exactly that for the robot arm video. And then it sits in a loop. In many ways, Arduino programs are quite similar to Pixel Game Engine programs. They have a one-fire method at the start and then something that sits in a loop. In the loop, all we're doing is waiting for data to arrive via the serial port, which in this case is the Bluetooth. We look at what the character was and we call the function. This implies that if we're choosing to move forwards, it will continue to move forwards until we send a stop command. Now, I've no idea what program is currently programmed on the car, and I'm not going to program it with this one. I'm going to take an intuitive guess that the pre-programmed program already running on the car's Arduino is likely to follow something very similar for the Bluetooth application on the Android phone. So I'm going to throw together a quick application that will allow me to send these bytes of data via a UART. I have a little Bluetooth dongle on my PC. As usual, I'm going to create a little Pixel Game Engine application to help us out. My intention is to create 4 on-screen buttons, which we can press to move the car or turn the car left or right. When we press those buttons, it will transmit some information via the Bluetooth connection to the car. I'm going to need 4 buttons, so I'm going to create a structure called S-button to contain the button's position on the screen, the size of the button, and the text displayed on the button. This information allows me to create a convenience function called clicked, which checks to see if a supplied position lies within the boundary of the button. I'm also going to have the button draw itself. Now, this is a common pattern in slightly larger projects, where you have components in the Pixel Game Engine that are some way responsible for their own appearance. And it pops up quite a bit on the channel and on the Discord how to handle this situation. Well, my approach is to create a draw self function where we pass in a pointer to the Pixel Game Engine. Now, my buttons are going to be represented by a solid blue rectangle in the background. I'm going to go all Final Fantasy-esque and give it a white border. And then to display the text in the middle of the button, I need to know how much space the text occupies. Well, the Pixel Game Engine provides functions to do this. It's called getTextSize. But the very latest version of the Pixel Game Engine has something extra. I'm going to use something called getTextSizeProportional, where we pass in the string that we want to know how big it is physically, and then we can use the drawStringProportional command to start drawing the string in the position where the middle of the string lies on top of the middle of the button. These drawStringProportional functions are new, and instead of every single character being drawn occupying 8 by 8 pixels, as is what happens with normal drawString calls, the spacing between the letters is dependent upon the letters, which allows you to draw far more normal looking strings that occupy significantly less space horizontally. I know for my application I'm going to require 4 of these button structures, and I'll create these on onUserCreate. For each button I'm setting the position of the top left corner and giving it a size. In this case they're all 100 pixels by 30 pixels, and I also set the text to be displayed on each button. In onUserUpdate, every frame I'm going to clear the whole screen to black and then call the button's draw method, passing in a pointer to this, which is the Pixel Game Engine, so that they can draw themselves. So let's take a look. Perfect. I've got 4 buttons on the screen and the button's text is central on the button. And here's a quick example of that proportional font spacing. See how the I in right takes up significantly fewer pixels than the other letters. Recall from the previous ASIO videos that we need to instruct the compiler where ASIO is installed on our system. So I'm doing that in the include directories of the project properties page. And I'm doing it for all configurations and platforms. This allows us now to include ASIO into our project, and I'm setting the ASIO standalone flag because it's not using Boost, and I'm also setting this WinSock deprecated no warnings flag. That's because the most recent version of the Pixel Game Engine deliberately excludes WinSock, and since part of ASIO fundamentally requires WinSock, we tend to get a little warning, so that will just suppress that warning. You'll notice that this time I'm not including anything TCP related. Serial ports are provided conveniently by the asio.hpp header file. When we're working with ASIO, invariably we're going to need an I/O context. And instead of a socket this time, we're going to be using an ASIO serial port. And in fact, I'm creating a unique pointer to an ASIO serial port, which allows me to construct it later on. We also know that ASIO will issue work to its I/O context. And this context needs to be given some space to do its thing. So I'll create a thread called thread context. As usual on this channel, I'm deliberately avoiding all sorts of error checking so we can focus just on what we need. Firstly, I'll need to create the serial port object itself, which is a unique pointer, don't forget. So I'll do port.reset and then create the new serial port object, associating it with the ASIO I/O context. ASIO has two main ways of reporting errors. One is it can throw exceptions, the other is it can simply return an error code. Keep it simple this time, I'm going to use the latter. Once the port is created, I'm going to attempt to open it. On Windows, ports are identified like this, COM3 and COM4. I happen to know that those two are the Bluetooth dongles on my computer. If you're unsure of the values, then I suggest you look through Device Manager and find out. If it failed to open a connection to the COM port, for example perhaps it doesn't exist, then we'll display the error code message and simply abort the whole program. On Linux, accessing COM ports is very similar, except they're not called COM1, 2, 3 and 4. They're usually something along the lines of /dev/ttyp0xz, loads of squiggles. Typical Linux stuff. If we get this far in our program, we can check to see if the port is open. And it's at this point we need to configure the port's behavior. And again, I will defer to the robot arm video for a more detailed explanation of what's going on here. But the first thing we should set is what is effectively the speed of the communications. The baud rate or baud rate, depending on where you're from. Configuring the port is done through the set option function. And for each type of configuration, ASIO provides a helper utility to make sure it's the right format. Now I'm going to take a guess that Elegoo aren't doing anything special with the communications and will be adhering to the standard 8N1 UART communications protocol. This means we want to set 8 as the number of bits per nugget of transmission. It's a byte. Again, we call the set option function and specify the character size. Now by default, we can see that this is already 8, so I don't need to construct this with any arguments. The number of stop bits by default is set to 1, and we'll set the parity, which by default is no parity. Finally, we'll set the method of flow control, which is none. I'm attempting to connect to a device which I haven't programmed. I'm just hoping, with my fingers crossed, that it's going to be sending some sort of meaningful data and responding to the data I'm going to send to it. Therefore, I've no idea when it's going to actually send any data at all, nor do I have any idea of the size of that data. It's almost as if I need to asynchronously respond to data that it sends. So isn't it fortuitous that we're using an asynchronous input-output library? We looked at setting up asynchronous communications in the ongoing ASIO series, where we're looking at building an MMO. And I do talk about that in some detail, but for this simple application, we're going to keep it simple. I'm going to create a function called asynchronous read from port. And since I don't know the size of the data, I don't expect it to be very much, I'm just going to respond to every byte individually that gets written. So upon my serial port object, I'm going to call the async readsum function. We looked at the socket equivalent in part 1 of the networking series. Any data that this function picks up will be placed into an ASIO buffer. So I'll create an ASIO buffer of 1 byte, and that 1 byte I'm going to store simply as a char in my class. Just like the networking series, we provide a lambda function that actually does something with the data when it receives some. The structure of this lambda function is just the same as it was before. And at this point, we've sufficiently abstracted the communications mechanism from our application. This now looks very familiar, and the contents of this lambda function don't care if it's come from a COM port, a serial port, or a network socket. I'm going to keep this very simple though. I'm going to make sure that no errors have occurred. I'll display the byte to the console window that runs behind the Pixel game engine, but I mustn't forget to then prime the ASIO I/O context with more work to do. In this case, try and read another byte from the port. When we've created the port up here, we need to prime the ASIO I/O context with this async read from port function. And then we can create our context thread to allow the context to do its work. Because the context has been primed with some work to do, it's not going to exit immediately. Now, the eagle-eyed amongst you out there may have noticed the onUserDestroy function. This isn't a function we typically see in most of the videos, but it is there as an overridable as part of the Pixel Game Engine and gives you a chance to clean up your project when the Pixel Game Engine is closed. Normally this doesn't really matter, but when working with communications and hardware objects, I always like to have the opportunity to actually close them properly. So the first thing I'll do is make sure that our port object has actually been made. If it has, then I'll call the cancel function on our serial port object, which will attempt to stop any communications happening at that time. I'll then physically close the port. Now, you might think that at this point we would typically erase the port by resetting the unique pointer, but we can't do that just yet. Don't forget, we're thinking asynchronously. Even though we've cancelled some communications and we've closed the port, there may still be some ongoing stuff using our port object, so we can't erase it just yet. Hopefully the cancel function will have informed the I/O context that the asynchronous job waiting for it to read data is no longer required. So we'll sit here and wait for that thread to expire naturally, because the context will have no further work to do. Once the context has expired, then we can erase our unique pointer for the port.
I want a way to sensibly test my application, and therefore I need a Bluetooth enabled device that can show me the bytes being sent to it, and I can also send bytes from it back to the application we're creating in the Pixel Game Engine. Fortunately, my phone is such a device, and I've downloaded an app that allows me to use the Bluetooth of the phone as a UART terminal. And here it is.
As you can see, I've launched the Pixel Game Engine application and I'm displaying the window in the background. And on the application on my phone, I have connected to my computer via the Bluetooth. This means I can now send it some messages. So I'll send it hello and press the send key. Well, it's sent, and we can see it's been displayed in the terminal behind the Pixel Game Engine window. Our application has successfully asynchronously received that data. Let's try something else. So, robot car, just to make sure, send it. Takes about a second, and there it appears. At the moment though, we never send anything to our Bluetooth device. So let's implement that. I'll start just by creating a little placeholder error code, and then I'll check the state of the left mouse button to see if it's been pressed. I'll then successively check the clicked method using the current mouse's location on each button, which will return true if the mouse is inside that button, and since we're already knowing that the mouse button has been pressed, we can assume it's been clicked. If it has been clicked, we need to then write a byte, and we can do that not asynchronously this time, with the port write some function. And in this case, I'm just going to send the letter F, because that's what the Android program was expecting to see as an indication that we should move the car forward. I'll then do this for the other buttons too. We've handled all 4 buttons being pressed, but at the moment this will send the event to the car and the car will keep moving. We must also send a stop command. And so I'll do that whenever the mouse button is released anywhere on the screen. This effectively makes all of our buttons momentary. So let's take a look. I've started the application, and I've started the application on my phone. I shall connect. There we go, we have connected, and we'll just do that quick test again to see if the data gets through to the computer. There we go, it does. And now, if I press the buttons, I press the forward button, we can see an F appeared. So this time I'll press and hold down. So F, and when I release the mouse, S. Try for left, L and S. Try for right, R and S. Backwards, B and S. Very good. So it looks like we've now got two-way communications via Bluetooth from the Pixel Game Engine to my phone at least. Now it's time to try it with the car.
And this is where I've hit a little bit of a snag. Here we have the Bluetooth module provided by Elegoo, and it turns out that this module is in some way hard configured to only talk to the mobile phone application. I can already hear the open source hacking community screaming, "Why could you do such a terrible thing?" But it makes complete sense from the point of view of a product manufacturer. This is the type of kit that you would buy children for, say, Christmas Day or a birthday, where it needs to get built up as quickly as possible and then simply just work. The battery came with a little bit of charge in it, the Arduino came pre-programmed, and all the end user needs to do is build the car, which as we've seen is quite simple, download the application, and they can start driving it about and looking at what the sensors say. i.e., it's just going to work. However, this limitation is no good for us. I can't connect to it with my PC. I need to replace it with another Bluetooth module. Fortunately, I happen to have one from my robotic arm project, and don't they look very, very similar? In fact, they are very similar. They have exactly the same pinout and exactly the same power requirements. So I'm going to take a chance and see if I can just pop mine in instead. But as you can see, physically it won't fit. So I'm going to use the smallest bit of breadboard that I have and simply bridge from the car over to my Bluetooth module. Now it's time for the moment of truth. I'm going to turn the car on and see if anything goes bang. Well, we can see that my Bluetooth module is blinking. That means it's waiting for something to connect to it. So I'm going to start up the application. Well, the application has started, and we can see that the light is no longer blinking continuously. So just to stop it not crashing into my camera again, I'm going to lift the car a little bit and send it a command. I'm going to click the forwards button. Very nice, and now I'll let go, and forward movement stops. Let's try backwards. Good. Left and right. So very fortuitously, that little Bluetooth program that we saw before is actually in some way installed on this car. So I'm going to try turning it now and see where it all falls to bits and goes horribly wrong. That's very nice, and it's very snappy and responsive, unlike the little infrared remote control we had at the start. I now think I have a chance of controlling this car over some sort of racetrack. And we might let the Twitch chat control that at some point over Christmas, because that was a lot of fun when we let Twitch control the robot arm. They almost killed me with a screwdriver. So there we have it. We have a Bluetooth controlled robot car provided by Elegoo, so again a big thank you to them. And we're controlling it via ASIO and the Pixel game engine. We've barely scratched the surface of what we can do with this technology. We've not used the sensors, we've not moved the servos, we've got the line following thing which we've not even looked at on the bottom, and the Arduino itself is quite capable with lots of I/O we have access to. As a little platform for exploring embedded programming and sensory algorithms in the future, I think this is wonderful. And I've put a little link to it below. It's been a quick fire one, but if you've enjoyed this video, give me a big thumbs up please, have a think about subscribing, and I'll see you next time. Take care.